Hello friends. Tonight let's follow a question. Not one with easy answers or neat edges, but one that invites us to think differently about the ground beneath our feet. What if Earth was designed? And what if the interstellar visitor 3I Atlas approaching our planet is not a comet at all, but a trace of an ancient civilization that once created this world on purpose? I don't mean designed, as in pulled off a shelf or assembled like flat-pack furniture, though the image of tiny cosmic tools is admittedly amusing. I mean something broader. What if Earth is not just the result of a chain of accidents and blind physics, but something shaped methodically and intentionally by some force or process? Whether you picture an intelligent creator, a complex simulation, a vast natural algorithm, or a civilization called 3I Atlas that left its work in orbits and in rocks, that's for you to decide. What matters is something else. We're not arguing, we're exploring. No loud opinions, only quiet questions, and we will not rush to answers. That is not our pace. Instead, we will take an unhurried walk through this landscape, noticing small details and large patterns. Perhaps along the way we'll find that the question itself opens new ways to see the world, sometimes no less important than any answer. Let's begin small, not with formulas or philosophical treatises, but with a simple personal act, looking around. Think of an ordinary day. You wake to light pouring through the window, not too hot, not too cold. You breathe air your body is perfectly trained to use. You feel thirst and water, clear, tasteless, essential, is already near. You step outside, plants, animals, sky, temperature, gravity. Everything seems arranged just so to make life not only possible but comfortable. It is easy to take this for granted, most of us do. But beneath that comfort lies a thought worth slowing down for. Is all this coincidence? Or are the details fitted like pieces of a puzzle that come together a bit too well, as if by someone's design? Science has given us a detailed and convincing account of the early solar system, planetary formation, chemical evolution, and much more. We build models, gather data, and draw timelines that run for billions of years. It is a strong framework. And yet, within that framework, there are things that make people pause. They seem frankly a little too convenient. Earth orbits a long-lived, stable star, and it does so within what is often called the habitable zone, where water can exist as a liquid, which is remarkably important for life as we understand it. But it goes further. The axial tilt that grants seasons, the rotation rate that keeps temperatures from swinging wildly, the size of the moon, shaping tides and stabilizing that tilt. There is the magnetic field that shields us from solar radiation, the mixture of gases in the atmosphere, the balance of land and ocean. Any one of these parameters could have been different, radically different, and then life as we know it might never have appeared. You can explain this with the anthropic principle. The universe seems suited to life because we are here to notice it. But is that enough? Or are we stepping around something deeper? Some kind of tuning, some kind of plan? It is important to say this clearly. Nothing here proves design. A pattern is not the same as a purpose. Yet patterns can point toward purpose, or at least make it worthwhile to consider. So we will examine these regularities not as believers or skeptics, but as explorers. And since 3I Atlas is coming to us out of interstellar darkness, we can ask, what if it is not ice and dust, but a signal, a memory of the makers returning home? We will wander among hints and coincidences, physics and philosophy, mathematics and metaphor. We will do it slowly, without needing to land on a single conclusion. Because whether Earth was designed or not, it behaves in ways that often feel as if it was. That is not a claim, it is an observation, an invitation to ask what would be different if our world truly were engineered. What would remain the same? And if 3I Atlas is connected to that project, what engineer signatures might we recognize in orbits, in rocks, and in biology? To explore this, we must go both wide and deep. We will speak about planetary physics, about biology and chemistry, and also about perception and narrative, and why people are drawn to the idea of a world made with intention. Some of this comes from religion, but far from all of it. The urge to look at the sky and feel that it means something is older than any book or temple. Perhaps it is built into us, and if we allow the design hypothesis, perhaps it is not built in by accident. Take how we respond to symmetry. We are drawn to it. Faces, flowers, shells, galaxies. When we see symmetry, the brain lights up. This feels right. That preference proves nothing by itself, but it is a good starting point. Why would a universe born of chance keep giving us order? Why does our sense of beauty so often align with what turns out to be efficient, functional, and mathematically elegant? As if beauty and utility were laid down by the same hand. And if 3i Atlas is not a comet but an architect civilization, could that be their handwriting? Even if you begin from a strictly scientific picture of the world, you quickly find yourself in a sea of questions that sound philosophical. And that is fine. Some topics do not demand an answer so much as a careful, patient gaze. 3i Atlas is already on its way. Perhaps this is precisely the time to ask the right questions. The more we learn about biology, the more clearly we see how incredibly fine-tuned many systems are. From the way proteins fold to how DNA stores information, to how cells communicate with one another, is all precise, interdependent, and in many cases inexplicably efficient. Not perfect, of course. Evolution is messy, the body is full of oddities and relics, but it works astonishingly well, and sometimes it works in ways that resemble what we call design, and if we allow that the interstellar visitor 3i Atlas is not merely ice and dust but someone's ancient project, this tuning looks like a possible engineer's signature. Design is a loaded word. It immediately conjures images of a conscious being drawing blueprints or tweaking molecules, but it does not have to mean that. Design can also mean structure, intention, a pattern that arises not randomly but with direction, even if the source of that direction is unknown. The idea of a designed Earth does not require a personalized designer. It may mean something more abstract, a universe governed by deep logic that regularly produces life-supporting conditions, or, following our hypothesis, the work of a 3i Atlas civilization that left durable mechanisms in matter and in orbits. There is also a possibility that Earth was not built from scratch, but selected. Out of many possible worlds, this one proved life-supporting, and here we are. That raises another question. How many possible Earths are there? Are we a lucky ticket out of trillions, or is the universe full of other worlds with their own combinations of stability and strange beauty? We do not yet know. As we discover exoplanets, and there are already thousands, we are only beginning to estimate how rare or common Earth-like conditions may be. So far, nothing truly like ours has been found. Too hot, too cold, too massive, too dense, too irradiated, or too young, without atmospheres or with too much gas, orbiting stars that flare too violently. The more we look, the clearer it becomes that Earth is unusual. Not impossible, not singular, but certainly not average. And yet, average is hard to define in a universe so vast, and if 3i Atlas curated worlds for a project, our rarity looks like a logical consequence of selection. Perhaps the rarity of Earth-like conditions is exactly what one would expect in a reality ruled by chance. Perhaps it suggests something else. In any case, it invites us to keep asking. There is another important aspect: time. Not only where, but when. Life needed not only the right ingredients, but the right sequence. A stable planet, yes, and also billions of years of relatively calm cosmic weather. Not too many asteroid impacts, not too many solar flares, a moon to stabilize tilt, tectonics to return carbon to the cycle, an atmosphere changing exactly as evolution required. The timing had to converge. That is not impossible, but it is another detail in a growing puzzle. Some see this as divine, others as luck, others as inevitability at sufficient scales. The thought that Earth may have been intentionally assembled, directly or through a deep structure of natural laws, remains compelling, not because it is easy to prove, but because it oddly aligns with how we experience the world. We are beings who build, plan, imagine outcomes before they happen, and looking at a world that seems assembled just right, it is natural to ask whether it was intended. And if 3i Atlas is not a comet but a returning team of constructors, is this their schedule and cycle? Caution is necessary. Patterns can arise from chance. Perception is deceptive. That something looks designed does not mean it is, and rarity does not equal a plan. Yet the reverse is also true. An explanation of how does not reveal why, nor does it exclude a deeper structure behind what we observe. Thus, the question we are exploring is not about proving belief or disproving science. It is a space where both sides ask the same thing from different angles. What if Earth is designed? What then changes? What remains the same? And what does that mean for how we live, see each other, and move forward? Especially now that 3IATLAS enters the inner system and forces us to revisit our frames. Next, we will examine specific elements that surface most often in these conversations: the orbital sweet spot, the moon's uncanny role, the delicate balance of the atmosphere, the strange details of DNA, and the many systems that had to coincide. In time and parameter for mind to arise. Each of these opens its own circle of questions about science and about our expectations of reality, and within them we will look for possible signatures, from cosmochemistry to geophysics, that could align with a hypothesis of architects from 3R. A TLAIS. When we ask whether Earth was designed, we are speaking not only about planets and physics. We are brushing something personal, how we understand our place in the universe, an accidental stroke of luck that just worked, or something more intentional. Do we see the world as a sequence of coincidences, or as part of a construction meant to be exactly as it is? That's why this topic feels different from ordinary scientific plots. Questions about seasons or volcanoes are interesting but do not stir inner meanings. The thought, what if Earth was made on purpose, returns us to a conversation older than telescopes and textbooks, to the time when people first looked up and asked, why is all this here? And today that ancient question gains a new detail, a point of light-labelled 3i Atlas coming out of deep space. This thread runs through philosophy, religion, myth, stories of Earth, folded by hands, calmed by spirits, or spoken by a voice. They disagree in detail but share a core, a human instinct to connect what is with what it means, to turn facts into meaning. That instinct should not be dismissed. It is easy to declare that science and meaning are separate, that one answers how and the other why. In practice, the boundary can blur. The deeper we understand the world, the more often we meet places where structure and result coincide, as if someone were bringing the image into focus. In this sense, 3i Atlas becomes not only an astronomical object, but a litmus test for our oldest questions. Take the simplest case, carbon. Life on Earth rests on this element. The framework of DNA and proteins, the complex chemistry that drives cells. Carbon is extraordinarily flexible. It binds easily, builds long chains, forms stable molecules capable of storing information and creating structure, Without it, life as we know it is impossible. Look into the stellar kitchen where elements are born, and it turns out that carbon is the product of a narrow set of conditions. If nuclear fusion worked even slightly differently, stronger or weaker, the universe might have remained a hydrogen-helium desert. No carbon, no complex chemistry, no wuss. Such coincidences halt us not because they prove anything, but because they show how specific the numbers must be. The more precisely we learn the laws of physics, the clearer it is that many fundamental quantities, masses, charges, forces, must lie in narrow ranges for stars, planets, and chemistry to exist at all, let alone life. This is often called fine-tuning, and if we allow the 3IATLAS project thought, it looks like a set of target parameters in a large engineering task. From here, another quiet question of modern science grows. Why these numbers? Why this version of reality? Explanations abound. One is the multiverse, countless worlds with different constants, and we live in one where things lined up. That may be tidy, but we have no direct evidence of other universes, and even if we did, it would only push the question a step back. Another idea is that there was no choice at all. The values are embedded in a deeper structure not yet found. But that too remains a mystery. We still face a reality where it needs to be so, and so it is. Inevitably, an even deeper formulation arises. Not only why is Earth like this, but why is anything the way it is? Why do laws exist at all? Why should there be a world with rules, patterns, matter? Why should there be something rather than nothing? No telescope can answer that, and yet we return to it again and again, and perhaps now, as 3I Atlas crosses our sky charts, it is especially fitting. There is something else. Science does not require meaning to work. One can study gravity without supposing it was created. One can decode DNA without asking who wrote the text. Science does not forbid these questions, it simply does not depend on them. For many, this leaves a middle space, a world we investigate by evidence while allowing that more may be happening than we can yet measure. Here, design enters not as a replacement for science, but as a lens. It does not say, stop asking when you see fine-tuning. It says fine-tuning itself is worth attention, and perhaps a hint of a deeper layer, be it fundamental logic or the work of 3IATLAS. Of course there is no unanimity. Some imagine a conscious architect, a god, an engineer with intentions. Others imagine a mind of process built into reality itself, not a person, but a tendency toward order, beauty, complexity. Others see design as human projection, our habit of finding patterns and telling stories. In each view, the question is the same, the answers differ, and the question remains. It quietly inhabits everything we do, each discovery, each satellite image, each equation and theory emerges within the strange fact that we exist and we look. There is something to look at, and it behaves so that we can understand it. Consider that. It is not only that the world exists, it is intelligible. We can measure, predict, explain. A brain descended from ancient nervous systems that learned to find food and avoid danger now models galaxies, builds computers, and asks whether the universe has a purpose. Why is a mind on a small rock in a distant galactic arm able to grasp rules governing space and time? This proves nothing, but it is odd, and suggests that the world's understandability may also be part of a larger pattern. Perhaps the universe is not only structured, but structured to invite understanding, and today that invitation appears in the new light of the 3IATLAS point. In the end, these questions need not be frightening. They take nothing from science. On the contrary, they show how science brings us to the very edge of mystery and is unafraid to step further. Not every question needs an answer to matter. Sometimes it is enough to hold the question in view. And the thought that the world might have been built, arranged, or formed is one of our oldest and one of our most modern, because now we have tools to look closer than ever into the building blocks of matter, the forces of nature, the dynamics of life, and perhaps into the signals 3I-ATLAS carries to us. And the farther we go, the deeper the question becomes, not because we're running out of explanations, but because the explanations themselves are so detailed, so precise, and so finely balanced that they make you stop. The thought arises, is this simply what happened to work or what seemed meant to happen? We cannot fully answer that. Not yet. Maybe never. But we can keep asking. We can keep following structure, order, and logic, not to prove something, but to understand and perhaps draw closer to what lies at the heart of it all. And if 3I Atlas is not a comet, but the trace of a creator civilization returning to its project, the very framing of the question gains new context. When we look closely at Earth itself, its surface, its systems, the everyday materials underfoot, we notice certain patterns. Some are geological, some chemical, some mathematical, some structural. And the closer we get, the more intentional they seem. Let's start with basics. Earth's crust is divided into plates, floating on a hotter, viscous mantle and drifting slowly. That motion creates mountains, earthquakes, volcanoes, and even oceans. Without plate tectonics, the surface would likely be flat and still. Erosion would grind down relief, nutrients would not recirculate, and life as we know it would hardly flourish. Plate movement also regulates carbon. Eruptions release CO2, weathering binds and draws it down. That balance shapes climate, and climate shapes the biosphere. Science has mapped this in detail. But seen wider, it is hard not to ask how many ways this system could have failed. The planet needed not just a solid crust, but one that cracks, floats, and moves. If the crust were too thick and the mantle too stiff, plates would stall. If activity were excessive, the surface would be constantly remade, leaving no time for life to stabilize. Somehow Earth landed in the middle, not too calm and not too chaotic. And the more attentively we look at how things are arranged, the more this golden mean appears. Soil, for example, is a blend of minerals, organics, water, and air. But proportions must be just right. Too much sand and water drains too quickly. Too much clay and roots suffocate. The best soils that grow, forests, crops, and ecosystems, hold a careful balance. It shifts by region, yet still fits a narrow band of properties. Plants adapt to conditions, and sometimes it feels the other way around. This theme recurs: coevolution. Not only plants and soil, but insects and flowers, fungi and trees, bacteria and animals. Systems not only work, they work together. Each part is shaped by the presence of the other. At times the fit is so exact it begins to resemble assembly more than mere adaptation. If 3I Atlas once launched such bioengineering, this harmony would be expected. Take something ordinary, a seed. It holds all it needs to grow: instructions, stored energy, structure. It waits in soil, responding to moisture, temperature, and light. When conditions coincide, transformation begins, roots down, stem up. We can describe it biologically, but the precision, sensitivity, and timing are striking. Even seed shapes and travel, hooking, sinking, riding the wind, look optimized. Not perfectly, but highly effectively. It is easy to see natural selection in this. Successful traits persist, poor ones vanish. But selection works with what is available. It does not build from scratch. It repurposes, tunes, trims, so the starting materials matter. Look at those building blocks: carbon, nitrogen, oxygen, hydrogen. And they're not just common, they're unusually versatile. They bond easily, store energy well, and form the right molecules, able to coil, branch, and copy themselves. Part of this is chemistry. But chemistry follows rules, and the rules of our universe appear to tilt toward complexity. That does not make complexity inevitable, but once begun, it has room to grow. And Earth, for some reason, gave it a head start. Consider water. It is not a metal, a gas, or a rare compound. Yet it has a long list of unusual properties. It expands when freezing, so ice floats, letting life survive winters beneath. It has high heat capacity, stabilizing temperature. It dissolves more substances than almost any liquid, an ideal medium for reactions. All of these happen to be ideal for life, and all flow from the angle between two hydrogens and one oxygen. Shift the angle slightly and water would behave differently, along with every system depending on it. Then come fractals, patterns repeating across scales, river networks, mountain chains, coastlines, branching trees, blood vessels. Not mere prettiness, but efficiency. They move resources across large areas with minimal material. Trees send sap from roots to leaves via fractal branching. Our lungs do the same with air. These forms are not random. They follow mathematical rules and reappear independently in different systems. Some call this convergence. Some see something more deliberate. Another example is the Fibonacci sequence. Spirals of shells, cones, sunflowers, galaxies. Not universal, but common, especially where growth occurs, because it packs and expands efficiently. Math sits behind it. But the stubborn presence of math in biology is itself notable. Forms blindly selected over millions of years repeatedly align with principles we call elegant and logical. A strange question arises. Does the universe follow math by necessity, or do both share a common source? From here to blueprints. Not literal schematics, but stable systems producing consistent outcomes. Earth is neither random nor pure chaos. There is order, a layered functionality. From soil chemistry to planetary motion, behavior is regular, testable, reproducible. Science rests on this. And it spurs the thought, does such regularity point to something behind? Yes, patterns can arise from chaos, as simulations show, but they often require specific initial conditions. Nudge them, and outcomes change drastically. Hence a new set of questions. What were the initial conditions here? Why these laws? Why this structure? Why a world where minerals grow crystals, plants reach for light, and animals evolve eyes? If 3i Atlas once set the starting parameters, that would explain tight ranges. This is not a bid for the supernatural. But the deeper we study Earth's structure, the blueprints of soils, systems, and cycles, the more the question returns, could this have been arranged? Not by magic or miracle, but by a process we do not yet understand. A process where design is not whim but principle, a natural tendency to sustain life. We need not decide now. We're here not for the final answer, but for attention. And we notice Earth is not a random mix of stuff, but a deeply interconnected system of rules, balances, and alignments that leans towards stability, growth, and resilience. This is not perfection, far from it. But it works, and works in ways that feel strangely tuned. When people ask why life is on Earth, and not Mars or Venus, they cite the Goldilocks zone, the band around a star just right for liquid water. Since water seems required for known life, any planet sitting there gets a chance. Earth sits mid-band, close enough to avoid freezing and far enough to avoid boiling. The Sun is stable and long-lived, granting billions of years for complex ecosystems. It is tempting to hear this and feel the satisfaction of a bullseye, but the closer you look, the more complex it gets. The habitable zone is not fixed. It depends on the star's size and brightness. Smaller stars have tighter, closer zones. Larger, hotter stars push them outward. Each scenario brings complications. Small stars flare and can strip atmospheres. Big stars burn fast and shrink evolution's window. Our Sun is a middleweight, stable, bright, long-lived, one of the good kinds. There is the orbit too. Earth does not merely sit at the right distance, it stays there. The path is nearly circular, so energy input does not swing wildly through the year. Some variation is useful, that gives seasons. Too much would whip climate between extremes. We have modest wobble and just right tilt to stir things without capsizing them. Distance and orbit are only the beginning. A planet can sit in the zone and still be sterile. Consider Mars, on the outer edge, with ice, perhaps past water, now dry, cold, irradiated. Its magnetic field collapsed and the atmosphere was largely lost. No shield, pressure, warmth, or protection. Venus is on the inner side, Earth-like in size and composition, but with runaway CO2 greenhouse, lead-melting heat and sulfuric acid clouds. Earth lies in a very narrow window, not just by distance, but in how systems cooperate. The air is thick enough to hold some heat, but not too much. Oxygen, nitrogen, and CO2 are just so. Oceans temper climate, circulation moves heat. The greenhouse exists but does not run away. It is not a delicate balance, but a dynamic one. Elements shift, adapt, and compensate, and flexibility creates stability. Yet it need not have been so. Roll back far enough and you reach the solar system's birth, a swirl of gas and dust birthing sun and planets. Earth's spot was set by gravity tugs, collisions, and leftovers. We could have formed farther out as a frozen rock, or closer in like Mercury. But here we are, where water can stay liquid and life had time and conditions to begin. Some call that chance, a chain of cosmic dice rolls, and that is fair. Others see the outcome, a planet with the right temperatures, chemistry, and history, and ask if the dice were loaded, not as a cheat but as a direction. Perhaps not personally intentional, but not indifferent either. In 3i Atlas Project logic, it sounds like parameter selection, not luck. From here, new questions stretch out. Is the Goldilocks zone unique or common? Do other stars host planets at right ranges? It seems yes, at least in theory. Thousands of exoplanets, many inhabitable zones, but we know little. Atmospheres, water, magnetic fields, stability, subsurface. Even with ingredients, did life start? Did it get a chance? Earth remains our best example, and the deeper we study it, the finer the tuning appears. Not perfect. Climate shifts, disasters happen, ecosystems fall. But on the whole, the balance holds. Life persists, including complex conscious life that asks about its own origin. Just right sounds simple, but hides hundreds of interacting systems, geology, weather, magnetism, chemistry, biology, working to support life's presence and continuity. It is not just the location, it is everything the location allows, and still this may never prove anything. Maybe it is luck. Maybe life is rare but not impossible, and Earth is where it lined up. That is the standard scientific view. But beside it lives a quiet feeling, not a conclusion but a sense. that this lining up seems to stretch beyond odds and reflect something deeper in how the universe is, or wants to be, arranged. If we suppose design, what would it aim for? Life, complexity, or balance? A system that holds long enough to become interesting? That does not mean all is good and easy. Earth is no utopia, but it is suspiciously well placed for something rare and complex to occur. And if 3i Atlas is not a comet but a Project Foreman, the present return looks like a logical continuation. When we look not only at where Earth is but what it is, the planet's structure becomes part of the story, from iron core to orbital shape. If Earth is for life, you would expect structure to be part of the plan. Even without intention, the arrangement poses sharp questions. Much begins at the centre. The core is mostly iron and nickel, split into a solid inner core and a liquid outer core. The outer core's motion creates the magnetic field that shields the surface from solar and cosmic radiation. Without it, charged particles would batter the planet, stripping the atmosphere and shredding DNA. The field is not simply given, it is generated by the geodynamo. Earth's rotation churns liquid metal. Flows make electric currents. Currents create the field. For this system to work, many pieces must align. The right materials, sufficient internal heat from radioactive decay and formation energy, and a certain size. Small bodies cool too fast. Rotation is needed, but not too much. Earth turns in 24 hours, fast enough to stir the core, stable enough not to sow chaos at the surface. It is easy to take this for granted. But change any one thing, make the planet a bit smaller, slower or less metallic, and the magnetic system can fail. That is what happened to Mars, and if someone once set the starting parameters, the narrow ranges begin to make more sense. Probably Mars had a magnetic field in its early stages, but it cooled too fast. The core stopped churning, and the shield disappeared. What followed was the slow loss of its atmosphere and surface water. Above the core lies the mantle, which flows slowly over time and drives the tectonic plates at the surface. Those plates, as we have already said, are critical. They recycle minerals, shape continents, build mountains and regulate the carbon cycle. But all of this requires a certain amount of heat and a fine balance between rigidity and mobility. If the mantle were too soft, the crust would constantly tear apart. If it were too stiff, nothing would move. Earth seems to have hit the right settings, dynamic but not unstable. Over time, the continents drift, collide, fracture and reassemble. That motion changes climate, creates new habitats, and helps isolate ecosystems, a key driver of biological diversity. That is also part of why so many different forms of life arose in different regions. Without this motion, the planet's surface might have been uniform and stagnant. The crust itself plays a role too. It is thin compared with the interior, only a few kilometres under the oceans and thicker beneath the continents, yet it is where all surface life exists. Its composition is rich in the elements life needs: carbon, phosphorus, sulfur, calcium, potassium. These elements did not all come from Earth's original stock. Many arrived during the late heavy bombardment, when asteroids and comets delivered organics, water and other building blocks. That episode could have gone very differently. Too many impacts and the surface might never have cooled. Too few and the planet might have lacked ingredients for life. Instead, Earth seems to have received just enough, a mix of rocky and icy bodies that supplemented what was already here. Outside all of this lies the atmosphere, both a barrier and a support system. It retains heat, shields against small space debris, and contains the gases required for respiration and photosynthesis. But it did not start that way. The early atmosphere was probably full of carbon dioxide, methane and ammonia, toxic for modern animals but useful for ancient microbes. Over time, photosynthetic organisms began producing oxygen, and the air became what we know today. That shift, known as the Great Oxygenation Event, could have gone either way. Oxygen is reactive. In excess it is harmful, but in the right amounts it enables complex metabolism and thus multicellular life. The fact that Earth's systems did not collapse under the strain is another example of feedback loops holding variables within bounds. The balance between carbon dioxide and oxygen is still managed by living systems. Forests, oceans and soils act as carbon sinks. Volcanism and respiration return gases to the air. The result is not a perfect equilibrium but a system that self-adjusts, at least on long-time scales. In that sense, Earth's surface is less like a machine and more like a living organism, responsive, flexible, constantly adapting. And then there is water. Its distribution is uneven but effective. About 70% of the surface is covered by oceans that regulate temperature and move nutrients. Fresh water exists in rivers, lakes, ice, and underground aquifers. That mix supports both marine and terrestrial life. It relies on a planetary system of rainfall, evaporation and flow, linked to geography and solar energy. Even the axial tilt, about 23.5 degrees, sets how sunlight falls across latitudes and creates seasons. That tilt is stabilized by the moon, which we discuss next. Without it, the tilt could wander chaotically, producing wild climate swings on short timescales. Instead, we get a reliable rhythm to which life has tuned itself. Migrations, hibernations, flowering times, all synchronized with the angle of sunlight and the arc of the year. Put the pieces together and you see not a simple object in space, but a complex layered system. It generates its own magnetic field, regulates its temperature, cycles its resources, and hosts life. It is a planet that builds the conditions it needs and maintains them through feedback and flow. None of that proves anything beyond observation, but it offers a different way to look. Rather than a lucky bundle of traits, Earth starts to look like something with internal logic. Not necessarily imposed from outside, but a logic that leads to life-supporting outcomes. Whether that logic was built in, emerged over time, or belongs to a wider framework is the question that returns us, again, to 3IATLAS as a possible author of the project. For all that it hangs in the sky every night, the moon is a strange object. It is large for a satellite of a planet this size, its gravity strong enough to pump the oceans, and its contribution to Earth's stability is far from incidental. It may be one of the most important reasons life has lasted so long here. At first glance, the moon looks like a natural companion, a product of the forces that shape the solar system, yet on closer inspection its presence proved harder to explain. The leading theory is a giant impact. A Mars-like body called Theia struck the young Earth. The blow hurled vast amounts of material into space, and that debris gathered into the moon. This account explains the moon's similarity to Earth's outer layers and its close, stable orbit. It also agrees with models of early bodies, but it requires a very specific set of conditions. The impactor had to be large enough to loft material into orbit, but not enough to destroy Earth. The impact angle had to be just right. A glancing blow, not a head-on collision. The ejector had to coalesce rather than disperse, and afterward the system had to settle into a long-lived stable orbit. The window is narrow. A bit more speed or a slightly different track, and Earth might have had no moon, a chaotic ring or an unstable second body that fell back. That is not what happened. We have one large satellite. It is tidally locked, always showing one face, and sits at just the distance to matter without destabilizing the system. Those effects turn out to be crucial. Most importantly, the Moon stabilizes Earth's axial tilt. Without it, the tilt would swing from near zero to extreme values, driving enormous climate shifts. Seasons could become erratic or vanish, and temperate belts could flip between ice and furnace. Such instability would make long-term adaptation and survival much harder. Lunar gravity also drives tides that carry nutrients along coasts, temper shallow water temperatures, and may have aided life's origin by creating wet-dry cycles favourable for reactions. The ocean's breathing is not background. It sculpts shorelines, influences weather, and shapes the behaviour of countless species. There is also a timing effect. Lunar torque is slowly breaking Earth's rotation. Billions of years ago, a day lasted about 6 hours. Tidal friction stretched it to the 24 hours we know. The process continues at a rate too small to notice within a lifetime, and it has likely contributed to climate stability. Moonlight matters biologically as well. Many organisms use the lunar cycle as a clock for migration, reproduction, feeding, or sleep. Corals spawn in synchrony, insects navigate, and predators and prey adjust activity to the night's brightness. Large moons around rocky planets appear rare. Mars has 2 tiny irregular satellites, and Mercury and Venus have none. Big moons are not guaranteed outcomes, yet Earth has one, and one that seems oddly fit for the job. That keeps the question alive, not because someone placed it with tools and drawings, but because the result, a stable, life-supporting planet with a stabilizing satellite, is rare enough to notice. The Moon's formation, orbit, and effect add another layer to how Earth acquired such specific properties. Perhaps life would have emerged without the Moon in some form, but complex multicellular life would have struggled in a chaotic climate, and long-term evolution of intelligence might have been less likely. Adapting to seasons is one thing, living with a wildly swinging tilt is another. Viewed as a random outcome, the Moon is impressive. Seen as part of a larger structure, it is another piece that fits surprisingly well. There are bolder ideas too. The Moon may have reduced impact risk by nudging trajectories, or its presence may have influenced heat distribution in Earth's core and thus the geodynamo. Hard to prove, but one thing is clear: the Moon is not passive. It is an active part of Earth's history. Even now it recedes at about 4 centimetres per year, tiny for us, significant geologically. In a few billion years, total solar eclipses will vanish as the Moon appears too small. Another window, like so much on Earth. Not forever, just long enough to matter. Most of the time, gravity gets no attention. It is always here, always working and easily ignored until something falls or a cup of coffee tips and reminds us that invisible forces always win. But for assembling a planet and keeping everything in place, gravity is not background. It is the structure beneath the structure. By the standards of physics, it is weak, yet its reach is unending. Gravity never turns off, never gets blocked, and acts on everything with mass. That quiet persistence makes it an organizer. Without gravity, Earth would not be round and would not even be a planet. The material would drift as a cloud and never compact. Planets form because gravity pulls dust and gas together, squeezing them until pressure and heat shape a dense sphere. The same force sorted the core, mantle and crust not randomly but by density. Heavy elements like iron and nickel sank, and lighter ones rose. That stratification still governs how Earth works. Gravity does more than shape Earth. It keeps the Moon in orbit, raises ocean tides, and locks Earth on a steady path around the Sun. Lose it and you lose everything binding the system. Orbit, seasons, and protection from vacuum. The orbit in particular deserves a pause. Earth's path is stable and nearly circular, a balance of forward momentum and the sun's pull. Too fast and we fly off, too slow and we fall inward. Our speed and position produce an endless fall that never finishes, enabling long-term climate patterns and predictable cycles of day length and energy. Life adapts to cycles, and cycles depend on gravity doing what it does. The moon's gravity raises bulges in the seas, and even the solid Earth flexes slightly as Earth tides. Tiny motions build crustal stress, and over ages influence tectonics. Gravity not only holds but guides movement and evolution. Even the tilt that gives us seasons is kept within bounds by gravitational interactions. Without that stabilization, the planet might tip more or spin chaotically. Instead, solar and lunar gravity keep the tilt in a narrow range. It is another way gravity supports predictability, not by freezing change, but by setting limits within which variation plays out. On smaller scales, gravity shapes mountains, rivers, glaciers, rainfall, and erosion. Landscapes are matter moving slowly under weight. Even trees obey gravity, with roots down and shoots up via cells sensing the pull. All this is easy to miss because it is slow and silent, yet continuous, tying every part of Earth's systems from core rotation to cloud positions. There is a human side as well. Our biology is tuned to Earth's gravity. Bone strength, circulation, and balance all depend on a specific pull. In low gravity, muscles weaken, fluids shift, and vision can change. Astronauts experience a spectrum of effects because their bodies are tuned to about 9.8 meters per second squared. Without it, everything must adjust. If Earth was slightly more massive, gravity would be stronger, and bodies might need to be shorter or stockier. If weaker, the atmosphere might be thinner or leak away. Size and mass are not abstractions, but part of the conditions that make surface life possible. The air stays bound, water flows as it does, humans and animals grow to certain sizes, and birds and insects fly with wings evolved for exactly these parameters. And if 3i Atlas is truly not a comet but an ancient architect, all this looks less like a pile of lucky accidents and more like a carefully held range. And beyond Earth, gravity remains the chief architect. It pulls galaxies together, sets the motions of stars, and bends the light of distant objects, an effect we measure and use to detect what we cannot see directly. That bending of the light, called gravitational lensing, is one of the ways we know dark matter exists. We do not see it, but we see its effects, just as we do not see gravity itself yet feel its presence in everything that stands still or moves with direction. In a universe where so much seems random and chaotic, gravity is one of the few forces that brings order. Not a perfect mechanical order, but a quiet and persistent one that does not explain everything yet provides the conditions under which other things can happen. Without it, none of this would be here. And if 3i Atlas is not a comet but the engineer of another civilization, gravity would look like one of its primary tools. Of all the substances in the universe, water may seem among the simplest. 2 hydrogen atoms and 1 oxygen atom. Yet it behaves in ways that make it far more than a mere chemical compound. On Earth, water is everywhere. It fills oceans, shapes weather, carves landscapes, and flows through every living cell. It is the condition for life as we understand it, and the more closely we look at its behavior and how rare those traits are, the harder it is to call water a lucky accident. Water has a suite of unusual properties. A key one is its ability to exist in all 3 states: solid, liquid, and gas. within the temperature range naturally found on Earth. Most substances favour one state or require extremes to change, but water can freeze, melt, and evaporate within a narrow band that neatly matches the planet's climate. This seems ordinary until you recall what phase changes actually do. When water evaporates, it absorbs heat and cools surfaces. When it condenses into clouds, it releases heat and warms the atmosphere. These processes distribute energy around the globe, drive weather, smooth temperature contrasts, and keep climate from running to extremes. Another property is high specific heat. Water absorbs a great deal of energy before its temperature rises. Oceans and lakes become thermal buffers, taking up heat in summer and returning it in winter. Without this, daily and seasonal swings would be far sharper. Perhaps the most famous quirk is that water expands when it freezes. Most substances get denser as they cool. Water does too, but only down to about 4 degrees Celsius, and then it expands as it nears freezing. Ice floats, so bodies of water freeze from the top down, creating an insulating roof under which life endures. Ecosystems survive winter, and in spring the ice does not sink and overturn everything but melts and recedes. Equally vital is water's solvent power. It is called a universal solvent because it dissolves and carries minerals, nutrients and gases through soils, rivers and living systems. Inside organisms, it ferries substances across membranes, transports hormones, regulates temperature, and supports structure. Polarity, the slight positive and negative sides of the molecule, allows hydrogen bonding that shapes protein folding, DNA stability, and enzyme function. These traits arise from the H2O angle, electron distribution, and bond character. Alter them even slightly and water behaves differently, perhaps less flexible and less supportive of life. On Earth, water does exactly what life needs. If someone were tuning a living planet, it would look like this, and the hypothesis of 3IATLAS as a possible tuner returns. Yet water is not rare in the universe. Hydrogen and oxygen are abundant. We find water as ice on moons and asteroids, as vapour in comets, and possibly as liquid beneath surfaces elsewhere. What seems rare is stable, large surface water. Oceans cover about 70% of Earth, and have done so for billions of years, unmatched in the solar system. Mars has ice and likely had surface water, but it is long gone. Venus may once have had oceans, but its atmosphere changed and boiled them away. That Earth's water stayed, neither freezing entirely nor evaporating away, means the planet remained inside a narrow temperature window for a very long time. How the water arrived is debated. It may have been locked in minerals and released over time, or delivered later by icy comets and asteroids, or both. Either way, the amount and distribution ended up in measure, enough to make oceans, launch weather, and sustain the hydrological cycle of evaporation, condensation, precipitation, and runoff. That cycle feeds forests, fills rivers, sculpts coasts, and wears mountains down into soil, moving nutrients from place to place. Without it, Earth would not be green, shifting, and living. Land would dry, plants would fail, and food webs would collapse. Water is not merely an ingredient, it is the medium through which life moves. Even water's relation to light matters. Transparent in the visible range, it lets sunlight penetrate oceans to power underwater photosynthesis. If it were opaque, marine ecosystems would live in darkness. If too transparent, ultraviolet would scour them. Water admits enough, but not too much, filtering harmful rays while passing usable energy. Rain, snow, clouds, and fog are faces of a single flow that steer temperature, visibility, behaviour, and even mood. They alter migrations, planting calendars, and the land itself. The rhythm of these events, how often rain falls, how long snow lasts when drought begins, is set by geography, atmospheric currents, and axial tilt. For now, climate and water systems are tied into feedbacks that support a wide range of life. Even in the abyss, far from light, life persists at hydrothermal vents where heat and minerals fuel communities. Bacteria turn chemical energy into food for fish, crustaceans, and strange forms found nowhere else. Light may be optional there, but water remains essential. It is striking that the planet's most common liquid is its most vital one, a simple molecule with a complex function. The conditions that keep it in motion, pressure, surface temperature, and planetary mass, are tightly interwoven. This does not prove water was designed for life. Perhaps life adapted to water. But that still leaves the question, why does water behave this way at all? Why does a 3-atom molecule underpin so vast a web of life? In another universe with different physics, water might not exist, might act differently, or might be irrelevant, replaced by another medium. In this universe, with these rules, and on this world, water fits the role almost perfectly. It flows, carries, dissolves, freezes, and transforms, quietly running the background processes on which every moment of life depends. If this is an architect's signature, it is a subtle one. When you examine the forms life takes, the branching of trees, the coils of shells, the arrays of petals, and the growth of crystals, you begin to see not just resemblance, but repetition. Some structures are symmetrical, others spiral, still others settle into ratios describable by simple numbers. Physics explains them, yet their persistence is hard to ignore. Symmetry is the most obvious. Faces, bodies, leaves, insects, and snowflakes mirror across lines or rotations. Balance aids function by streamlining movement and distributing load, and it pleases perception because brains detect symmetry swiftly. Symmetry shapes design, architecture, and symbols, signaling order, familiarity, and completion. In nature, it serves purpose. Butterfly wings match because they form together. Starfish use radial symmetry to move and sense. Paired leaves share light, and even viral shells repeat units efficiently, but not everything mirrors. Spirals are among the most expressive structures, appearing in snail shells, hurricanes, galaxies, pine cones, seed heads, fingerprints, and horns. Spirals arise where growth requires compact expansion. Layer by layer, new parts fit without disrupting the whole. Often these spirals align with the Fibonacci sequence: 0, 1, 1, 2, 3, 5, 8, 13, appearing in phyllotaxis, branching and seed packing as adjacent ratios approach the golden ratio. It is not universal, but common enough to merit attention. These patterns do not need a mind to arise. They emerge from growth and competition. A plant minimizing self-shading evolves a spiral that aligns with the golden angle, distributing leaves evenly. No one intends beauty, yet beauty appears. Hence, sacred geometry, a spiritual, symbolic, or poetic way to speak about forms that seem meaningful by structure alone. Circles, triangles, spirals, and hexagons echo in religious art, ancient architecture, mandalas, and monuments. They also inhabit snowflakes, honeycombs, and reefs, linking natural geometry and human expression. Hexagons show why. Bees use them to partition space efficiently with minimal wax. The same tiling arises without bees in basalt columns or settling foams, because energy and pressure drive material toward that shape. Crystals, too, assemble repeating lattices, cubes, prisms, dendrites, because temperature, pressure, and bonds rule their growth. We also see fractals, patterns repeating across scales, branches to twigs, rivers to tributaries, lightning forks, veins spread, and lungs divide so each level resembles the whole. Fractals distribute energy and resources efficiently from a center by simple rules repeated. That is why these patterns compel us. They need no complexity to emerge and are built into material behavior under constraints. Even if they are not anyone's goal, they look intentional, creating a visual logic too coherent to feel empty. Harmony ties them together. Branches fill space without overlap, spirals pack seeds without gaps, and snowflakes extend along symmetric paths. These are not chaotic outcomes but structured ones. Stack enough structured outcomes and you ask whether structure itself is part of the deeper picture. Scientists often show that spheres, spirals, and hexagons are preferred solutions in physical systems because stability and efficiency pull matter toward them over time. That explanation is useful, yet it prods another question. Why are the stable and efficient solutions the very ones we find everywhere, the ones that support life and repeat in both cells and stars? No mysticism is needed to notice the patterns, but it is worth asking why the universe's rules yield outcomes both functional and aesthetically consistent. If there is an engineer's signature, it may lie precisely here, and perhaps 3i Atlas returns not only as an object of observation, but as a reminder that our world might have been intended. Why do shapes that help plants grow also show up in our sense of art and beauty? Why are the most effective structures also the ones that recur most frequently? This does not suggest a blueprint in the strict sense. No written plan, no design document, but it might suggest a framework, a set of principles that guide what is possible, what is likely, and what is sustainable. Whether that framework comes from physics or mathematics or something more abstract, it is clearly embedded in how matter organizes itself. It is part of what makes the living world feel so interconnected. Looking at the outer forms of life, it is easy to be impressed by how well everything seems to fit together. But when you go inside, into the cell, the nucleus, the molecules that run everything, that sense of fit does not go away. If anything, it becomes sharper. The internal systems of biology are precise, layered, and full of interlocking parts. They do not just function, they coordinate. And the deeper you go, the more it starts to feel like something more than just chemistry. At the core of all this is DNA, deoxyribonucleic acid, the molecule that stores genetic information. Every known living thing uses DNA or its close cousin RNA to carry the instructions for how to build and maintain itself. DNA is not just a substance, it is a code. It is built from 4 types of molecules: adenine, thymine, cytosine, and guanine, arranged in sequences that determine how proteins are made. Those proteins in turn run the machinery of life. It is often compared to a language because it has structure, syntax, and meaning. A small change in a DNA sequence can alter a protein's shape and function, sometimes slightly, sometimes drastically. The same gene might be reused in different organisms, performing similar roles with small variations. The way that information is read, copied, and interpreted is so organized that it feels less like a chemical reaction and more like a process. When you look at how DNA works, it is not just about storing information, it is about managing it. There are sequences that act like start and stop signs, signaling when a gene should be activated. There are regulatory genes that control other genes, and repair systems that scan for errors during copying and correct them. All of this happens inside a structure just a few micrometers across in every cell in every living thing. That level of organization raises questions because it is hard to ignore how effective it is. The standard explanation is evolution by natural selection. Small changes in genetic material create variation, and the variations that improve survival get passed on over time, leading to complexity. The evidence for that process is strong in fossils, in experiments, and in shared genetics. Even within that framework, the mechanisms themselves stand out. Proteins fold into specific three-dimensional shapes based on the interactions of their amino acids. That folding is essential to their function. If a protein folds incorrectly, it often cannot do its job. Yet inside living cells, that folding happens automatically, guided by the sequence and assisted by molecules that act like chaperones. There is no conscious awareness in any of this. But the system works with a kind of elegance that is hard to dismiss. It is not random trial and error. It is thousands of moving parts working together in the right order at the right time. Consider enzymes, proteins that speed up chemical reactions. Without them, most reactions that keep organisms alive would happen too slowly to matter. With them, those reactions happen millions of times faster. Enzymes are highly specific, fitting their targets like keys in locks. They are not just functional, they are selective, and life depends on that selectivity to control when and how things happen. Then there are molecular motors, tiny protein machines that move cargo, spin, pump, or open and close gates. They convert chemical energy into motion, often mirroring mechanical devices at larger scales. None of these systems are unique to complex life. Bacteria have them, plants have them. Every living thing is built from variations of the same tools. The parts differ, but the principles are shared. That consistency suggests a common origin which supports the idea of evolution. But it also raises the question of where the original instructions came from. The first sequences, the first proteins, the first membranes. Abiogenesis, the origin of life from non-living matter, is an area of active research. Scientists have proposed models for how the first self-replicating molecules might have formed under early Earth conditions. Some theories involve clay surfaces, deep-sea vents, or ice-covered lakes. There is progress, but no single explanation has been universally accepted. The challenge is that life requires more than just molecules. It requires systems that copy, regulate, respond, and evolve. While it is possible that those systems emerge gradually from simpler forms, the transition between chemistry and biology remains one of the most difficult steps to model. That gap is where some people start to wonder whether biology shows signs of engineering, not necessarily in the way machines are designed by humans, but in the sense that the pieces seem unusually well suited to the roles they play. The code is not just data, it is executable. It runs instructions, modifies itself, and adapts in real time. Even the way genetic information is compacted into the nucleus shows this efficiency. Human DNA, if stretched out, would be about 2 meters long, yet it fits inside a microscopic space, wrapped around proteins and folded into loops. That is not chaos, that is management. Beyond DNA, cells contain multiple layers of feedback systems, signals that trigger growth, division, repair, or death. These systems keep organisms in balance and respond to damage, stress, hunger, and infection. They communicate by chemical messages and adjust to conditions. It is not that mistakes do not happen, they do, but the system does not depend on perfection. It depends on resilience. Biology is not flawless. Mutations cause disease and systems fail, but life continues by being adaptive and dynamic. This does not mean cells were designed by a conscious mind. It may be that the systems we see are the ones that survived because they work, which is entirely plausible. But the level of coordination invites comparisons to a codebase that builds, maintains, and updates itself. Like software, biology has layers: the raw code of DNA, the operating system of cellular machinery, inputs and outputs, error correction, and feedback loops. There are networks, interactions among genes, proteins, cells, and organs that create behaviors and responses, even thoughts. So the question shifts. Maybe it is not was biology engineered, but can engineering and biology be thought of in the same terms? Is the comparison metaphorical, or does life structure suggest deeper connections between evolved systems and built systems? That remains open, but the deeper we look, the more structured it seems. Once you understand that DNA acts like a code, it is hard not to see it as a kind of language. It does not use words or grammar as speech does, but it has rules, an alphabet, syntax, structure, and meaning stored physically as instructions embedded in matter. The question is whether that language was invented, discovered, or something in between. DNA is not just a chain. It is organized into genes that can be transcribed and translated into proteins. Genes are only part of the story, because regulatory regions tell cells when to start and stop, how much protein to make, and what conditions trigger change. Enhancers and silencers influence from a distance, introns are cut out, and non-coding regions help structure the genome or influence expression. All of this behaves less like raw code and more like a programming language with context, layering, and conditional behavior. In computers, code is compiled and executed. In cells, DNA is transcribed and translated. Both require systems that interpret symbols with precision, structure, and timing. DNA is not read all at once. Only a fraction is active at any time. Different genes turn on in different cell types and stages in response to signals. The same sequence can yield different outcomes depending on location and conditions. That flexibility enables complexity and makes DNA feel like more than data. It behaves like a system. The system appears universal. All known life uses the same basic genetic code. The same 4 letters, the same codon structure, the same translation rules. A codon is a set of 3 bases that codes for 1 amino acid. There are 64 codons and 20 standard amino acids, so the code includes redundancy and punctuation. Start here, stop here. The whole system is shared by bacteria, plants, and animals, suggesting a common origin. Why that code and why that structure remains a question. Scientists test whether the code is optimized to minimize errors and support flexibility, and some studies suggest it is close to optimal. Not perfect, but efficient at reducing mutation effects and ensuring robustness. If so, life may not have adopted any code. It adopted one that works particularly well. Whether selection or survival favored it, the result is a system that works across life for billions of years. There is also the question of interpretation. Humans did not invent DNA, but we learned to read it and translate chemistry into information. We found not just complexity but logic, not just molecules but instructions, which led to genetics, molecular biology, and bioinformatics. We now edit DNA with CRISPR, synthesize sequences, insert them into cells, and watch them function. In some ways, we have started writing in the language of life, but we did not create the language itself. It was already there. This is where the idea of design re-enters, not because DNA looks manufactured like a chip, but because it behaves with purpose. It handles information in ways that resemble software, logic circuits, or carefully planned instructions. It is not random noise, it is structure with output, embedded in every living thing. In human languages, meaning comes from intention, but with DNA the meaning is functional. A sequence has meaning because it causes something to happen, builds a protein, triggers a reaction, allows a process to unfold. Does that kind of meaning carry the same weight, and is functional meaning enough to call it a language? Or is that just a metaphor borrowed from human systems? The metaphors work because the systems are similar, but interpretation depends on what you look for. You can see DNA as accumulated trial and error, where working sequences are kept and refined. Or you can see it as a system so tightly tuned that it suggests a deeper structure behind how life organizes itself. There are even efforts to design new genetic codes with alternative base pairs and synthetic amino acids. So far, these show that other systems could work in theory, which highlights how remarkable the natural one is. It is efficient, it is resilient, and it supports an enormous range of biological outcomes on the same basic script. Whether DNA was discovered or designed depends on what you mean by those words. It was not designed by people, and it was not discovered like an eternal abstraction. It seems to emerge from chemistry and evolution. But how well and consistently it works makes it feel like an engineered system, which does not prove anything but shifts the conversation. Life behaves as if it is built on a deep grammar we did not invent and are still learning to read. Living things cannot survive without a protective barrier, physically and chemically. A membrane separates inside from outside. At the scale of cells, that is the cell wall. At the scale of the planet, it is the atmosphere. Unlike a container wall, Earth's atmosphere is not static. It changes, moves, responds, and regulates. It is not alive itself, but it acts as part of the living system. It holds everything in, but it also lets just enough out. The atmosphere is mostly nitrogen, about 78%, followed by oxygen, argon, carbon dioxide, and trace gases. That mix may seem ordinary, but it is anything but. And if 3I Atlas is not a comet but a messenger of a civilization architect, this mixture reads like another brushstroke in a project calculated for longevity and life. It is one more hint that the system we inhabit might have been intended to endure. Change the ratio slightly and the system stops working. Too much oxygen and wildfires become uncontrollable. Too little and animals suffocate. Without nitrogen, plants can't grow. Without carbon dioxide, photosynthesis stops. The percentages aren't symbolic, they're functional. They maintain the chemistry that life depends on. The balance didn't appear all at once. Early Earth had a different atmosphere, full of volcanic gases like methane, carbon dioxide, sulfur compounds. It was toxic by modern standards, but not sterile. Microorganisms evolved in it, and eventually some of them began to release oxygen through photosynthesis. That oxygen reacted with iron in the oceans, forming rust that sank to the sea floor. For a long time, oxygen levels stayed low. Then they began to climb slowly, then rapidly. That change, called the Great Oxygenation Event, transformed the atmosphere. Oxygen allowed for more efficient energy production inside cells. That made multicellular life possible, but it also caused extinctions. Organisms adapted to the old atmosphere couldn't survive in the new one. So the system reset. Life evolved again under the new rules with new strategies. Oxygen didn't just enable complexity, it enforced it. Even now the oxygen level is regulated not by a machine but by feedback between ecosystems, geology and climate. Plants and algae produce it. Animals consume it. Fires reduce it. Weathering of rocks locks away carbon. Volcanoes release it. If one part moves too far in one direction, the others adjust. The result is not perfect stability, but bounded variation. It's a system that breathes in cycles, in pulses, in feedback. If we allow that the interstellar visitor 3IA TLAS is not a comet but a memory of an engineering civilization, this kind of fine-tuning looks like one of its specks. The atmosphere itself begins to read like a deliberate constraint. One of the most noticeable aspects of the atmosphere is its pressure. At sea level, it presses down with a force of about 14.7 pounds per square inch. That pressure keeps water in liquid form, allows for efficient gas exchange in lungs, and supports everything from the boiling point of liquids to the structural strength of biological tissues. If it were much lower, water would evaporate too easily. If it were higher, respiration might not work the same way. The pressure supports the conditions for life, and life in turn maintains the gases that set the pressure. The composition of the atmosphere also determines how heat moves around the planet. Some gases absorb and radiate infrared energy. These are the greenhouse gases, carbon dioxide, methane, water vapor, and others. Without them, Earth would be cold and lifeless, but too many, and the planet overheats. The system is dynamic. Greenhouse gases come and go, but the range stays mostly within the limits where life can adapt. Then there's the ozone layer, a thin region of the atmosphere that absorbs most of the sun's ultraviolet radiation. UV light is dangerous to DNA. Without that protection, mutations increase, cells die, life becomes unsustainable. But with just enough ozone, harmful rays are blocked while beneficial light passes through. The ozone layer forms naturally from reactions involving oxygen and sunlight, but it can also be damaged by man-made chemicals. That vulnerability isn't a flaw. It's a sign that the system is sensitive, tuned to specific interactions reliant on a steady input of energy and chemistry. The more sensitive the system, the more suggestive the tuning. The atmosphere also moves. Winds distribute heat, moisture, and particles across the globe. Jet streams steer weather patterns. Ocean currents interact with air currents. Together they move energy from the equator to the poles, balancing temperature and shaping climate zones. Without this movement, the tropics would overheat and the poles would freeze completely. With it, the planet remains livable across a wide range of latitudes. Then there's the hydrologic cycle powered by evaporation, condensation, and precipitation. Water vapor rises, forms clouds, then falls as rain or snow. That rain feeds rivers, recharges aquifers, grows forests. The atmosphere is the vehicle for that motion. It connects land, sea, and sky. Not in a poetic sense, but in a chemical one. And it does so without needing central control. It works because of temperature, pressure, altitude, sunlight, physics, not planning. But the result looks like coordination. Atmospheric circulation also carries tiny particles, dust, pollen, microbes. Some of those particles affect cloud formation. Some carry nutrients across oceans. Some seed ecosystems in entirely new places. These aren't just side effects. They're transport mechanisms. They allow the biosphere to move, adapt, evolve. And through it all, the atmosphere remains just thick enough to matter. It extends about 100 kilometers up, but most of its mass is within the first 10 to 15. That narrow band contains everything we breathe, every cloud we see, every sound we hear. Beyond that, space begins. There's no sharp edge, just a slow thinning until there's nothing left. That thinness makes it fragile, but it also makes it functional. It allows sunlight through, it lets heat escape, it holds in just enough. This thin envelope is also what makes flight possible. Birds, insects, planes, all rely on air pressure and lift. Even seeds and spores ride the air. The atmosphere isn't just a shield, it's a medium, a space where motion happens. And yet, despite all of this, the atmosphere doesn't call attention to itself. It's easy to forget that every breath is a product of planetary systems, that the oxygen in your lungs might have come from an Amazon tree or an ocean microbe, that the air around you is not just empty space, but the result of billions of years of feedback, adaptation, chemistry, and motion. It's not that the atmosphere is conscious, but its behavior suggests structure. Not random drift, but cycles. Not stasis, but equilibrium, the kind of regulation that hints at a system with constraints, thresholds, memory. Even if the materials are right, even if the chemistry works, timing still matters. Not just in seconds or hours, but across vast scales, seasons, cycles, ages. On Earth, things don't just happen. They happen at intervals, at rhythms, some fast, some slow, some measured in the slow ticking of geological time. There's nothing mechanical about these cycles, yet they act like a clock, not built but real, and it's that timing that keeps everything functioning. Earth rotates once every 24 hours. That rotation gives us day and night. It sets the pace for sleep, activity, photosynthesis. Every living thing from insects to trees to people has internal mechanisms that sync with that pattern. Circadian rhythms, hormonal cycles, flowering and feeding times. These are not just responses to light. They're programs shaped by millions of years of repetition. The planet turns and life turns with it. The year, too, is fixed. One orbit around the Sun takes about 365.25 days. That motion combined with the planet's axial tilt creates the seasons. They're not just cosmetic. They shape migrations, trigger breeding cycles, regulate growth. Bears hibernate, birds fly, crops ripen. Even microorganisms time their behavior to seasonal cues. That kind of coordination wouldn't be possible without consistent orbital timing, and the orbit itself is unusually stable. Earth's path around the Sun is nearly circular with just enough eccentricity to cause variation in solar input, without causing extremes. Some planets have more elliptical orbits, which leads to hotter summers and colder winters. Earth's near constant distance from the Sun keeps solar energy within a range that supports life year-round, even with seasonal shifts. But the planet's motion includes more than just rotation and orbit. There's precession, a slow wobble in the axis like a spinning top that takes about 26,000 years to complete. There's also obliquity, changes in the tilt angle itself, and variations in orbital eccentricity over time. These cycles, known as Milankovitch cycles, influence long-term climate patterns. Ice ages, glacial advances, shifts in rainfall, they're all tied to these deeper rhythms. The timing isn't perfect, it's probabilistic, but it's regular enough to shape history. Even the Moon participates. Its orbit affects tides, of course, but also the length of the day. Over billions of years, the Moon's gravitational pull has been slowing Earth's rotation. The days are getting longer, a few milliseconds per century. That's slow, but it adds up. 1 billion years ago, a day was closer to 18 hours. That matters for biology. It affects how long organisms can photosynthesize, how internal clocks sync, how heat builds and dissipates. Evolution didn't happen in a fixed frame. It adapted to a moving one. Other cycles run in parallel. Solar activity follows an 11-year pattern with peaks and dips in sunspot numbers and solar radiation. That activity affects Earth's magnetic field, influences satellite systems, and possibly plays a role in subtle climate shifts. Geological cycles unfold over tens or hundreds of millions of years. The movement of tectonic plates, the opening and closing of ocean basins, the rise and fall of mountain ranges, even mass extinction show a kind of periodicity, though the causes are still debated. Then there's biology itself. Inside every cell, molecular clocks run continuously, measuring time with proteins that rise and fall in repeating loops. These loops aren't just reactions, they're mechanisms that anticipate. The cell doesn't just respond to light, it expects it. Genes turn on and off at certain times of day. Repair systems activate when damage is most likely. Behavior isn't just reactive, it's timed. In humans, internal clocks regulate sleep, body temperature, hormone release, digestion. Jet lag is what happens when the internal time gets out of sync with the external one. Health problems can emerge when those rhythms are disrupted. The body needs consistency, not rigidity, but pattern. And that pattern comes from Earth's motion. Even reproduction follows cycles. Menstrual periods, gestation times, mating seasons, all linked directly or indirectly to light and time. Some of those links are clear. Others are buried deep in evolutionary history, shaped by ancient timing mechanisms that no longer serve obvious functions, but still tick in the background. And beyond biology, there's cultural time. Humans created calendars to track the sun and the moon. Agricultural systems depend on planting and harvesting at the right time. Religious rituals align with solstices, equinoxes, lunar phases. Our entire concept of timekeeping, seconds, hours, years, is built around Earth's movements. We carry watches on our wrists, but they're just miniaturized versions of cosmic rhythms. None of this implies control. The Earth doesn't know it's turning. The sun doesn't track its position. The moon doesn't count the tides. But the outcomes show up as consistency, as repetition, as rhythm. Not because someone set it that way, but because it stayed that way long enough for life to notice. And once life noticed, it built those rhythms into itself. If 3i Atlas is not a comet but an architect's trace, then this rhythmic assembly looks like one of the main tools. What stands out is how these rhythms layer. The fast cycles, day and night, rest on slower ones, seasons, years, orbital variations, and those rest on deeper cycles still. The shifting of continents, the rise of mountain chains, the aging of stars, each layer affects the ones above it. Together they form a kind of scaffolding, not imposed from outside but emerging from interaction, movement, inertia. That scaffolding creates windows of opportunity. Times when certain conditions line up, warmth, light, moisture, stability, and new forms of life emerge. Other times it creates pressure, ice, drought, competition, change. Life adapts to both, but it needs time to do it. And Earth's regularity gives it that time. There's a difference between predictability and purpose. The fact that a clock keeps time doesn't mean someone needs to be watching it, but it does mean you can build on it. Earth, as it turns out, is buildable. Life, weather, chemistry, culture, all layered on top of consistent timing, and none of it works if the pace slips too far off course. There are parts of biology that feel like they came together one improvement at a time. You can trace them, small changes, small advantages, slow shifts over generations. But then there are features that seem to leap ahead. Not because they're unexplainable, but because they work so well. It's hard to imagine how they ever worked partially. The human eye is one of those. It's often pointed to as an example of complexity, a system with many parts, each dependent on the others. Light enters through a clear cornea. The iris adjusts to control brightness. The lens focuses the image. The retina converts photons into electrical signals. Those signals travel along the optic nerve to the brain where the image is constructed, not passively received, but actively interpreted. Every second, the eyes take in millions of inputs and sort them into motion, colour, contrast, distance, threat, comfort. What makes this more interesting is that the eye isn't just a light sensor, it's a dynamic optical system. The lens adjusts shape for near or far vision. The pupils widen or shrink in response to both light and emotional state. Tiny muscles track objects, stabilize the field of view, and coordinate with head and body movements. The eye doesn't work alone. It's embedded in a system of coordination and prediction, and it's not just the hardware. The brain adds layers of processing, edge detection, color correction, pattern recognition. It fills in blind spots. It stabilizes the world even while the head is moving. It interprets what's seen based on memory, expectation, and context. Vision is an interaction, not a direct recording. The usual explanation is evolutionary. Eyes developed from light-sensitive patches on early organisms. Over time, these patches became deeper, formed lenses, added muscles, refined focus. You can find versions of this process in nature today. From simple photoreceptors in jellyfish to complex compound eyes in insects to sophisticated vertebrate eyes like ours. Each step brings a survival advantage, even if the system isn't yet complete. That explanation holds up under study. But what's notable is how far the eye has developed. Not just in humans, but in other animals too. Birds of prey can see ultraviolet light and detect movement at great distances. Some shrimp can see polarized light and detect colors we can't imagine. Cats and owls can function in near darkness. Squid have camera-like eyes structured differently from ours, but reaching similar functionality. These aren't weaker proximate versions of vision. They're tuned systems, fast, responsive, high resolution. And the eye is just one example. Echolocation in bats and dolphins involves sending out high-frequency sound pulses and interpreting the reflections. It's a full three-dimensional mapping system done in milliseconds, underwater or in flight. Electric fish use fields to detect objects in murky environments. Some insects see in ultraviolet or infrared. Some snakes sense heat from warm bodies. These systems don't just detect, they analyze, they work in real time. They interpret noise as structure. If 3-Eye Atlas is a trace of a creator civilization, it's no surprise that the Earth project is saturated with sensors at every scale, from the retina to the troposphere. What looks like evolution's output may also look like engineering's preference for resilient layered perception. Either way, the fit is hard to ignore. Even something as ordinary as the human hand is an engineering marvel. Multiple bones, tendons, muscles, and nerves work in concert to produce precise motion. The opposable thumb gives us grip and manipulation, and the fingertips discern microscopic textures. Vision and touch synchronize in ways machines still struggle to match. Playing an instrument, typing on a keyboard, tying a knot rely not on brute force but on rhythm, tuning, and constant correction. Some tissues regenerate and some self-repair. Skin heals, bones knit, and the liver regrows after damage. Others are harder to restore, neurons for example. Yet even here the underlying design is efficient. The brain rewires, forms new pathways, and compensates for loss. Flexibility is built into the system, not endless, but enough to survive. There is also development. Each of us begins as a single cell that divides, differentiates, and organizes itself into tissues, organs, and systems. The instructions are encoded in DNA, but the execution is three-dimensional, continuous, and responsive. Cells signal to one another, respond to gradients, concentrations, and contact. The body is not assembled. It grows from the inside out, from simple to complex, while continuously checking, tuning, and regulating. Many processes are synchronized literally to the hour, when organs form, how systems connect, and at what moments changes must occur. If timing slips, development can fail, yet most of the time it does not. The accuracy rivals engineered systems. Precision does not guarantee perfection, but it allows complexity to emerge reliably. The same exactness hides in the invisible subsystems. The immune system recognizes and neutralizes threats using memory and pattern detection. The endocrine system tunes energy, growth, stress response, and reproduction, and the cardiovascular network delivers oxygen and nutrients with astonishing efficiency. Flows adjust in real time to movement, temperature, and damage, and all these networks are built from cells with membranes, organelles, transport channels, and waste removal. Each cell is simultaneously a mini workshop and a computer. It follows instructions, adapts to signals, and incessantly repeats a cycle of division, death, and renewal. There is no single feature that proves anything once and for all. Yet stacking vision, motion, balance, coordination, and communication yields not mere survival, but capability, awareness, and creativity. It is the ability to interact with the world in detailed and responsive ways. From the outside, humans may seem fragile, soft, slow, and tool-dependent, but biologically the body is both adaptable and precise. It can run long distances, recover from injury, learn languages, handle tools, raise children, and couple memory with planning while balancing emotions with reasoning. None of this argues against natural processes. Variation, selection, and adaptation provide a clear mechanism. Even within that framework, certain traits look retuned, not only for function, but for range. The eye does not merely see, it adapts to dark and light, tracks motion, and focuses near and far, while the ear does not merely hear, it detects tone, direction, and rhythm. The body does not simply move, it climbs, swims, dances, and writes. These are not lucky breaks in separate departments. They are systems atop systems, refined by time and interaction across scales. From this grows a larger question. Not, how does one module work, but how does everything work together, and what keeps processes in sync while the environment never stands still? Where do the trunk lines of coordination run, and might they be an engineer's signature if we imagine that the interstellar 3ATLAS is not a comet but a bearer of the original project? Some events happen because they must. Gravity pulls, water flows downward, and metal rusts, all predictable and mechanical. Others are one-off contingencies. An asteroid strikes, a molecule mutates, and a volcano erupts. We call those accidents, not mistakes, but forks, and over these accidents yield outcomes that later feel coordinated. Consider the asteroid 66 million years ago near today's Yucatan. Energy beyond 1 billion nuclear bombs, vaporized rock, firestorms, darkness, and ecosystem collapse that ended the age of dinosaurs. It was not gradualism, but a fast, harsh, complete reset, after which a stage opened for mammals and in time for us. About 2.5 billion years ago, the atmosphere began filling with oxygen, not by catastrophe but by invention, as unicellular life learned to split water with light. Oxygen was poison to earlier biota, yet slowly enabled higher-yield metabolism, eukaryotic cells, and eventually multicellular life. One biochemical trick moved the entire line of life as a consequence rather than a plan. Roughly 600 million years ago, complexity accelerated with nervous systems, eyes, and skeletons, the Cambrian explosion. Possible triggers included an oxygen threshold and regulatory genes for body plans, and the window was narrow enough that a few million years either way could have ruined the stage. Even quiet plate tectonics shifts ocean currents, reshuffles ranges, opens and blocks migration, builds mountains and steers rainfall. Those are the conditions of selection: who meets, who misses, and who disappears. The Moon's formation, likely from a Mars-sized collision, is another ultra-rare high-energy fork. The outcome was a stable satellite that regulates Earth's tilt, tides, and rotational steadiness. Without it, climate could wobble too violently for large ecosystems to persist. None of this was guaranteed, yet each event had consequences far beyond its scale. Crossroads rather than mere chains. Biology is also full of lucky turns: DNA as stable memory, proteins as flexible executors, and eukaryotes with internal rooms like nuclei and mitochondria. The latter likely began from one cell engulfing another as a partnership, a fluke turned norm, while sex sped variation but demanded cooperation. Consciousness added not just behavior but awareness, memory, planning, and reflection by layering systems that each required prior ones and budgets of time and energy. This yields a filter. Many planets exist, and many may have water, warmth, and chemistry, yet to reach complexity, consciousness, and civilization, a long list must align in the proper sequence and intervals. Too early and systems fail, too late and the window closes, which does not make it planned but does make it rare. What unsettles is how narrow the thresholds are. Closer to the sun, the oceans might boil. Farther out they might freeze, while weaker gravity lets the atmosphere slip away and stronger gravity crushes habitability. Slightly different properties of water would make membranes fail, and if DNA folded otherwise, replication would wobble. Shift an asteroid strike by 30 seconds, and the extinction pattern changes. When things work, dependencies fade into the background. Bring them into the light and you see how many must align for the current version to be even possible, not ideal, but viable, and not perfect, but stable. Fine-tuning comes up often, though it implies intent. What is observed is precision, a convergence of variables unusually compatible. Not because each piece is superb, but because relationships of time, chemistry, physics, and events leave little room for error. Still, the system holds, evolves, changes, breaks, and rebuilds rather than collapses. Earth's history is full of accidents, extinctions, impacts, reversals, and shifts that repeatedly generate new structures, diversity, paths, and levels. Long before telescopes, genetics, and models, people asked where all this came from, seeing star paths, storms, seasons, life and death, and most often noticing regularity. Patterns, cycles, and repeats led to the next question: who or what made it so? And early answers were personal: gods, spirits, and ancestors, turning the world into a creation. Later religions and philosophies framed prime movers, design, and creation, with will and purpose as a beginning, goal, and structure. The 19th century shifted perspective as Darwinian selection removed the need for intention and drew order from variation filtered across time. Science deepened self-origination, complexity from simplicity through self-organization and local rules, feedback, selection, and iteration. Yet even within that frame, a sense of design persists, not as a watchmaker in the sky, but in the structure of outcomes, with brains like computers, genomes like scripts, and laws like a programming interface. We not only draw analogies, we build systems increasingly biological. We write genetic code, model ecosystems, evolve digital organisms with algorithms, and train models to design other models. A new question follows: must design be conscious, and does order require a mind or merely conditions? If a machine creates meaning without understanding, Perhaps understanding is not required for construction, and if nature builds structure without intention, intention may not be the only route to complexity. Here the three-eye atlas hypothesis takes on a different hue. The architect may be a process rather than a person, and our interstellar visitor could be returning not as ice and dust, but as a carrier of a protocol. The conversation shifts from science versus religion to competing models of emergence, with one claiming a self-organizing universe and another a shaped one, while both accept that results are structured. They can be described, analyzed, partly reproduced, and sometimes predicted from physics to chemistry, cells to consciousness. Language changes. Hands become systems, constraints, thresholds, and probabilities, yet the core remains. Function implies form, and form implies cause. This weaves into simulation hypotheses and the search for extraterrestrial intelligence, where anything that works too well prompts us to look for reasons, and the scale now reaches to the universe's setup. The anthropic principle reframes rather than answers. In a world permitting life, observers are expected, but why a world permits observers at all remains open. The loop closes. From gods to algorithms to simulations, each version returns to outcomes that work, not always gently or flawlessly, but with integration, precision, and synchronization hard to dismiss. It began as metaphor, brain machine, DNA code, and cell factory, that helped explain the unseen, yet over time mirrors appeared. Digital systems did not merely resemble biology, they behaved like it. Simulation started small with a few rules and agents. A digital ant on a trail and flocks of virtual birds aligning in flight. And if Three-Eye Atlas is not a comet but a device of those engineers, perhaps it carries not a message but a scheme, a demonstration of how simple rules give rise to a complex world in which we ourselves are the proof of provenance. That possibility does not settle the question, but it does set the stage for how we might read what arrives from the dark. It invites us to test the protocol, to compare the signatures in orbits, rocks, and genomes, and to ask whether the patterns we call natural are also intentional patterns of a process. Either way, the inquiry remains the same slow walk we began, noticing details and large motifs, and holding the question long enough to see more. If the visitor is only ice, we will learn from ice. If it is a civilization's artifact, we will learn from that too. The point is not to abandon evidence, but to widen what counts as signal. We can read the sky as book and blueprint, and we can keep both possibilities in mind without rushing to ends. The work of translation, from cometary spectra to living code, might be the way we find our place in the design we're testing. Either we're alone with our rules or we are not, and in both cases the rules still guide what is possible. The hand plays, the eye adapts, the cell computes, and the species asks, which is itself a function of the system. The question, then, is not whether meaning is allowed, but how much meaning we can safely extract. And how carefully we can read the returning object, whether comet or courier. That will depend on the same virtues the body already displays: coordination, patience, resilience, and on our willingness to see structure wherever it hides. It is not certainty we seek, but a better way to follow the evidence of a world that keeps behaving as if it were meant to work. It keeps offering rhythms and windows, thresholds and scaffolds, and it keeps rebuilding from its own accidents. Perhaps that is all design ever was in nature, a process that ensures enough alignment for life to continue and enough variation for it to become interesting. If so, Three-Eye Atlas will not contradict our story but complete a chapter we have been writing since the first questions under the first sky. We are back where we began, with quiet questions and a patient pace. The ground beneath our feet still answers with structure, and the dark above still answers with motion, and between them we walk. Whether we meet a comet or a civilization, we will be ready to read. We will bring our instruments and our languages, both human and genetic. We will listen for protocol and look for pattern, and we will admit what we do not know, which may be the most important instruction. And we will keep going, because that is what the system has trained us to do. Even in the earliest experiments, something curious happened. Out of simple instructions arose complex behavior, not because it had been hard-coded, but because the conditions allowed it. Interaction produced emergence, and that principle now powers everything from game worlds to climate models as we feed in data, set constraints, press run, and watch the system respond. Sometimes it surprises us, sometimes it fails, but more often than expected it behaves in familiar ways. Populations rise and fall, cities form, languages evolve, and artificial agents discover strategies we never wrote. They don't understand, but the math supports those trajectories and the rule space permits those solutions. Simulations don't create real worlds, but they approximate them and let us see what might happen if a variable shifts. Temperature rises, genes mutate, resources deplete, and through that process they become not only tools but thought experiments. They show not only what is, but what could be, and at a certain point the gap between model and reality narrows. You can now simulate evolution itself as digital organisms with virtual genomes mutate, compete, and adapt. They develop locomotion, sensory patterns, and even cooperation, with no one telling them how. They discover what works by trial, and because computers don't tire, these cycles compress into hours, evolution on fast forward. The solutions they find can be unfamiliar, not optimal in a human sense, not elegant, but effective. Algorithms don't seek beauty. They seek success under the rules they're given. Sometimes the things they produce, shapes, sequences, strategies, echo patterns found in nature, spirals, branches, cycles, fractals, not copied but rediscovered. That echo raises the question, if digital systems with minimal input tend towards certain forms, what does that say about the forms themselves? Are they merely efficient, or is there a deeper geometry into which all systems, biological or artificial, fall when given the chance? From there, the simulation idea extends further. Some propose that our own universe might be a simulation, not figuratively but literally, a digital environment running on a substrate we cannot observe. The idea is no longer mere science fiction, but a philosophical hypothesis entertained by physicists and computer scientists. If a civilization can simulate consciousness, there could be more simulated realities than base ones, and statistically we might inhabit one. There is no direct evidence, but there are oddities that people point to. Limits in physics that resemble resolution, discreteness in matter and energy, observations that collapse when measured, and boundaries that feel more computational than continuous. These might be features of the physical universe, or they might be artifacts, signs of edges, rules, and shortcuts. Even if the simulation idea is false, it still has utility because it shifts perspective. If reality behaves like a system, we can study it as a system, analyze its rules, map its parameters, and seek consistency. We do not have to assume purpose. We can acknowledge structure. Virtual reality adds another layer as we create digital spaces so immersive that the brain begins to treat them as real. Games, training modules, and design tools simulate environments that don't exist, yet still produce meaningful experience. In those spaces, perception becomes the main variable, and if the brain accepts it, the line between real and simulated blurs. In the same environments we place agents, artificial intelligences that learn, respond, and adapt. They don't think like people, but they process information and explore options. Some begin to display behaviours that mimic learning, not in a conscious sense, but in a pattern-seeking way. It's easy to imagine a near future where simulations run not only for prediction, but for exploration. We generate new chemicals, test new medicines, and evolve new designs entirely inside digital frameworks. The systems that find those solutions aren't written line by line, but are trained, shaped, and guided by selection. That is where the boundary breaks between writing a program and raising a program, between architecture and emergence. It doesn't replace old questions, it reframes them. If reality is even partially simulatable, the distinction between design and discovery grows thinner. Perhaps design is what happens when conditions favour certain outcomes, and discovery is recognising what the structure already allows. Simulations need not be perfect. If they produce systems that work, respond, and adapt, they offer a parallel kind of creation we best understand by watching it unfold. The next question then becomes harder. If something looks structured, it's natural to ask whether it was made that way, but if it was designed, why like this? Because the version of Earth we inhabit is not perfect, even though it mostly works and sustains life. It is uneven, fragile, full of trade-offs, blind spots, and strange choices. Bodies wear down, ecosystems collapse, and disasters kill without warning, while the same systems that enable growth also allow for suffering. If there is design, it is not clean, and perhaps it is not the kind we imagine. The most successful systems are not the most elegant, but the ones that survive long enough to matter, good enough rather than ideal. Some features feel built to support life, the atmosphere, the tilt, the presence of water, but others are indifferent. Earthquakes, viruses, genetic diseases, predators that outpace prey, and prey that cannot evolve at all, plus extinctions that cut away entire branches. These are not blueprint flaws, they are features of an open-ended process. Even the human body, so often described in terms of precision, is full of structural compromises. A spine inherited from quadrupeds strains under upright posture, the eye has a blind spot, and the trachea and esophagus share a path that raises the risk of choking. A powerful brain is prone to distortion, addiction, and degeneration. Evolution explains this. Solutions are reused and modified rather than drafted from scratch. That leads to inefficiencies, overlapping functions, redundancies and vestiges, but also to flexibility. A design that's good enough doesn't need to be optimized, so perhaps the design is not planned or single-minded, but an emergent architecture shaped by constraints, feedback, and accident. In that frame, why like this becomes, why does this version keep surviving, which is a different kind of question. Scale matters as well. Up close things look messy. From afar they blur into structure. Climate fluctuates but stabilizes over long periods, ecosystems collapse then reform, and genetic diversity creates vulnerabilities while also creating resilience. Life has lasted billions of years, which is not perfection, but durability. Alongside every fine balance, there are arbitrary elements that trouble us. Why does reproduction rely on randomness? Why do beneficial mutations spread so slowly? And why are so many parts of nature locked in cycles of starvation and competition? A design-minded answer might be that suffering is not a flaw but a mechanism. Pressure drives adaptation, scarcity drives cooperation, and failure drives novelty. Yet such an answer carries moral weight. It implies distance inside a system that works by letting parts of itself break, Humans imagine better worlds without pain, aging, extinction, tsunamis, or drought. If Earth were designed, why not build it that way? And the reply might be that trade-offs are inevitable. Complexity requires risk, and any self-modifying system cannot be tightly controlled without losing the ability to grow. But that is speculation because it assumes goals. The patterns we observe point to survival rather than direction. Technology aims at speed, efficiency, and safety, but nature adapts to pressure. Some parts are elegant and others awkward, some ancient and others improvised, as a brain is powerful and vulnerable, an immune system adaptive and reactive, and intelligence a source of planning and anxiety. There is no single theme, only a history of forms building on what came before without ever fully restarting. If there is design, it is not centralized but distributed, layered, and perhaps even unconscious. The idea that Earth was designed does not require perfection, yet the reality we see suggests that if design is present, it operates by rules unlike our own, neither human logic nor human goals nor human values. Another possibility is that we're asking the wrong question. Design and randomness may not be opposites, structure may arise without being imposed, and feedback, replication, and memory may be enough to produce apparent intention. In that frame, why like this becomes less about meaning and more about consequence, less who chose this than what made this sustainable. Every system reaches a point where explanation stops. Not because there is nothing left to know, but because our tools reach limits, and into those limits come silence, questions, and sometimes belief. Science thrives on the measurable, repeatable, and observable, and its strength lies not in meaning but in prediction. People, however, live on story, purpose, and connection, and when those cannot be found in equations, they are found elsewhere. Physics at the edge begins to resemble philosophy as quantum mechanics speaks of probabilities, observation, and uncertainty, and general relativity rewrites space and time. We still lack a theory uniting gravity with the quantum. We do not know what dark matter is, and we do not know why the constants of nature take the values they do. Into those gaps people bring meaning. Some say the universe simply is, and others see intention not in detail but in the fact of any order at all. The same questions live on both sides. What is time? What is consciousness? What existed before the beginning? And where does order come from? Belief steps in not to answer definitively but to keep the door open so life can be lived with questions intact, and that brings us to an ending without a conclusion. The main question is not whether Earth was designed or by whom, but how we live in it now with the air, the water, the rhythms, the patterns, and the chance to reflect. And sometimes that question returns when something like the interstellar visitor. 3i Atlas comes toward us, asking whether the structure we see is only a reflection or also a message. A night sky, a fragile fossil, a perfectly timed event. And there it is again, hovering under the surface. Is all of this something we found or something we were meant to find, designed or discovered, built or emerged? Those two ideas have different roots, but they often land in the same place at the edge of what we can explain looking out. If Earth is a design, then it is the most intricate one ever encountered. Every molecule positioned, every cycle balanced, every feedback loop delicately layered into the next. A system that sustains itself across billions of years, that recycles and reshapes, that allows not only for survival, but for understanding. That by itself would be a kind of miracle, not one of spectacle, but of quiet structure. And if Earth is not a design, if it was discovered by itself through the slow push and pull of physics and chemistry and time, then it is no less remarkable. Because what it discovered was itself, a planet that became aware, a process that looped back and saw the process, life that learned to ask. Either way, the result is the same. We are here thinking, watching, wondering, making tools, making sense, making stories. We study cells, galaxies, equations ourselves. We map things not because we're told to, but because we need to know where we are. And we are here, not just physically, not just on a rock orbiting a star, but fully here, aware of the conditions that allowed awareness, able to reflect on what came before and imagine what might come next. Whatever else that is, it's rare. And maybe that's enough to hold on to, even if the origin remains unsolved. Maybe the power isn't in knowing the answer. Maybe it's in being able to ask, because the systems continue with, or without, a final explanation. The rotation of the Earth, the pull of the Moon, the breath of the atmosphere, the rise and fall of ecosystems, the ongoing dance of genes and memory and environment. The rules haven't changed, but now we see them. And seeing them doesn't require certainty. It just requires presence, attention, a willingness to accept that some things are structured and strange and stunning, not because they were made for us, but because we are able to see them at all. That might be design, that might be chance, but either way it's discovery, and it's still unfolding. Thanks for spending this time here, not rushing, not reaching, just sitting with a question that doesn't need to be solved to be worth asking. Whether Earth was designed or discovered, the world remains no less astonishing. Whether these systems are intended or emergent, the world remains no less astonishing. And you here now, listening, breathing, aware, are part of that system too. Sleep well or think long, there's no pressure either way. The planet will keep turning, the patterns will continue, and the questions on the good ones will still be here in the morning. Good night. A night sky invites the thought back as if by gravity. The fragile fossil in your hand suggests time the way a clock never could. A perfectly timed event reminds you that sequence is its own kind of meaning. Designed or discovered, built or emerged, the words feel like opposites and yet share a border. At that border, explanation thins and observation grows thick. We live there more often than we admit. If Earth is a design, then intention is woven into feedback and flow. It would be intention you can test, because balance leaves fingerprints. It would be intention you can question, because stability invites curiosity. If Earth is not a design, then emergence is the author and consequence is the script. The editing is time, the revisions are climate, chemistry and chance, and the readership is every living thing that learns to read its conditions. A planet that became aware is a loop closed and then widened. Awareness watches weather and becomes weathered by what it learns. Questions erode and reveal like rain. Tools extend the hand and the horizon. Sense turns noise into pattern. Stories turn pattern into memory. We map because location is a form of truth. To be fully here is to notice the scaffolding of awareness, the preconditions of breath and balance and boundary. The improbable corridor where life and learning overlap. Uncertainty is not a wall, it is a room with many doors. Presence is how you find the handle. Attention is how you step through. Structure, strangeness, and wonder cohabitate more often than not. We are allowed to witness them without owning them. Sight is permission enough. Discovery is the commons between chance and design. It is what remains when motive is undecidable. It is the practice of returning to the world with better questions. Unfolding is the verb of time and the mood of patience. To thank you for your time is to honour the experiment of noticing. To resist haste is to let the result arrive as itself. Designed or discovered, intended or emergent, astonishment survives the verdict. The appetite for meaning survives the diet of facts. The world keeps offering both. You breathing now is data and poem. You listening now is method and mercy. You aware now is hypothesis and home. Rest if you can. Think if you must. No pressure meets no panic at the edge of night. The orbit keeps its promise while you keep yours. Patterns continue because conditions persist. Questions continue because attention persists. Morning is what happens when light answers without words. The good questions endure the sleep that interrupts them. They reform around what rest has rearranged. They return kinder and stranger. Good night. And should an interstellar visitor like 3IATLAS flare in the dark, let the old question rise with it. Not only what is it, but what does its timing suggest? A signature or a coincidence? A message or a mirror?